Math 2415, Calculus 2, Multivariable Calculus. Chapter 10, Vectors in the Geometry of Space. Section 8, Arc Length and Curvature. Video 2, Example of Arc Length. We're going to find the length of the arc of the circular helix with vector equations RT equals cosine t, sine t, t, from the point 1, 0, 0 to the point 1, 0, 2 pi. Of course, this is a vector equation, just has multiple component functions. Before we find this arc length, I do want to confirm that this is a circular helix, which is like a spring, if you will, by analyzing the component functions and seeing how they interact with each other. Specifically, we have x equals cosine of t. We have y equals sine of t. We have z equals just t. Well, we can tell from the component equations for x and y that x squared plus y squared is equal to 1. Meaning, if we totally ignore the z component for a second, we get the cylinder, x squared plus y squared equals 1. Remember, what makes it a cylinder is that this equation is deficient in the sense that it doesn't have a z component, which means we can view this as a graph in the xy plane. Of course, that would be the unit circle. So pretend that has a radius of 1. But because this equation makes no mention of the z coordinate, then the z coordinate can be any point, any z that I want, as long as it's above, below, or on that unit circle in the xy plane. So in other words, we actually do get a cylinder, a circular cylinder, if you will. But what about the z component? Well, the z is whatever the angle is we're putting inside of this parametric, these parametric equations. So for example, if z equals 0, if t equals 0, then we get cosine of 0, which is 1. T equals 0. Let's try that again. How about we type it? What a novel idea. We put t equals 0, we get cosine of 0, which is 1, sine of 0, which is 0, and then the z component is just whatever t is, which is 0. So this curve is going to start at 1, 0, 0, which will be out here, where it intersects the positive x-axis. And as we move upward, we go around the circle, but we're also elevating. And if we make one complete cycle, in other words, one complete period, if you will, and go t equals 2 pi, where does that put us? Well, due to the periodic nature of trig functions, namely that the period of cosine and sine is 2 pi, the x and the y component functions are going to be the same, but the z component will be 2 pi. Strictly in the, hold on, there we go. Strictly in the xy plane, as the t increases, we just rotate around the circle. Going in a counterclockwise direction, which in this perspective would be going this direction around the circle. But as we're going around that circle, the value of t is also increasing, and hence the value of z is also increasing. And so we're actually going to go around this and make a little spiral as we go up here. And when we make one complete revolution, we'll be back above the original starting point of 1, 0, 0. We'll be at 1, 0, 2 pi. Now, in drawing this, I accidentally, or maybe not, figured out what values of the parameter generated these 2 points. But if we wanted to find the values of the parameter that generated these 2 points, the initial and terminal points of this curve, all we would have to do is look in the z component, because the z component tells us the value of the parameter. It's not always that straightforward. We could have equivalently said cosine is equal to 1. Well, that's a bunch of places. But sine is also equal to 0. Okay, well, that puts us at any angle coterminal to 0 radians. But the t component, the z component clearly holds what value parameter we currently have. All right, so we're finding the arc length of this helix, if you will, as I shift colors and draw the axes blue and my little spiral red. Okay, not the best spiral I've ever drawn, but it'll go. All right, so for our arc length formula, we need to integrate the square root of the sum of the squares of the derivatives of the components. So in other words, we need to figure out what r prime of t is. Well, that's easy. We just take the derivative of the components. The original x component was cosine. Its derivative is negative sine of t. The original y component was sine. Its derivative is cosine. And the original z component was t, but its derivative is 1. And so now that we have the derivative, we need its magnitude, and we're going to integrate that. The magnitude of this Sorry, sometimes when I'm typing, I don't mess with the arrows, but by context, you can tell R is a vector function. The magnitude is the square root of the sum of the squares of the components. Well, the square of the first component of the derivative is sine squared of t. The square of the second component is cosine squared t. And the square of the third component is just 1. But last time I checked, as every Cal 2, Cal 3, Cal 1 student should know, sine squared plus cosine squared is equal to 1. So under the square root, we have 1 plus 1, aka 2. And we end up getting the square root of 2. From a physics perspective, that means that our speed is constant as we move around this helix. The velocity isn't the same because the direction changes, but the magnitude of the velocity, aka the speed, is still the same. But regardless, our arc length is now the integral from the first value of the parameter 0 to the last value of the parameter 2 pi of the expression that we just got, but we just got the square root of 2. Well, this suddenly became easy because the integral of a constant is just that constant times the variable being evaluated from 0 to 2 pi. If we put in 2 pi and put it in front, we get 2 pi square root of 2 minus square root of 2 times 0, which is 0. So the arc length is 2 pi square root of 2. Something for you to think about. Here's a follow-up question. What would the radius of the circle have to be in order for this arc length to be 1? So this is just a little something for you to ponder. It's not for bonus points. It's not part of any assignment. It's just, this is how mathematicians think. I wonder if I can control my arc length and make it equal to 1. So what radius would yield an arc length of 1? In other words, a unit arc length. That's just something for you to think about. If you want to work it up and write it up, I'd love to see it. Maybe I'll give you some bonus points for it.